Pleasure to be here by reading dinner, I think. So this cartoon shows the orbits of a few thousand of the more than 1 million asteroids that are out there orbiting the solar system. And the blue circle, if you can see it, if you can see this, does this mouse appear now? Okay. Oh yeah, right. Okay, right. This is the orbit of Earth, this little blue ellipse here, and Mars is the green ellipse here, and Jupiter is that this green ellipse out here. And what you can see is that many asteroids orbit between the orbit of Mars and Jupiter, but many also cross the orbit of the Earth. And really every day there are pieces of rock from these protoplanets entering the Earth's atmosphere and making craters and things. And they're also hitting other places like the moon. And speaking of the moon, we really did go to the moon back in the 60s and collect samples there. And those samples, you may be wondering what happened to those samples. They're still on Earth here in the Johnson Space Center in Houston in a very clean laboratory. And today I'm going to talk about not only lunar samples that we curate here in Houston, but also other kinds of samples from outer space. These are called astromaterials these days. And there's 3 ways to collect astromaterials. One way is to wait for them to come to you. We're talking about recent meteorite falls. Meteorites fall really every day. Mostly they fall in the ocean or in places where no one notices. But sometimes they fall on driveways or houses or people, and then they recover very quickly. You can also collect past meteorite falls on the Earth, and there's something like 70,000 meteorites that have been collected on the Earth, mostly in deserts. I'll talk about those as well. And finally, you can go out into space and collect these things for yourself. That's pretty expensive, but NASA also does that. And we'll discuss that also. So all these materials are being curated around the world, and a lot of them are being curated here in Houston, starting with the Apollo samples, which were collected in the late 60s and early 70s by astronauts. And also there was some robotic missions from the Soviet Union, and those samples are here in Houston. And you astronauts really go to the moon and collect these samples. And I guess they had fun. They had fun doing it, right? And those samples, you might wonder what happened to those samples. They're still mostly here in Houston and also around the world in laboratories. They're in special vaults we have here next door to where I am right now. And they're handled in a clean room that's about as clean as an operating room. So if you've had your appendix out or something, it's the same kind of environment. Samples are kept in nitrogen cabinets, and they're handled by highly trained scientists. If you want to analyze these samples, you can request them, and if the peer committee agrees, then you can come to Houston and pick out the samples for analysis. So they're kept here, and even after 60 years, we're still learning new things from these samples. It's just the past year, one of the lunar cores was opened. Those astronauts collected about half a dozen core samples by driving piston tubes down into the lunar surface, and they pulled them out. And these are basically samples of the subsurface of the moon. We get some idea of the order in which things happen on the surface, the order in which impacts happen, volcanic eruptions, things like that. And several of these core tubes have never been opened, even after 60 years. You know, I opened one of them just this past year. Pretty exciting. And here's this is actually like an X-ray image of the interior of the tube. It's like a CAT scan of your body. Only this is a CAT scan of rocks inside a metal tube. And this gives the scientists an idea of where to look in this tube for different kinds of samples. So it's been exciting happening over the past year. Speaking of asteroids and meteorites, if you want to go collect asteroids and meteorites, where would you want to go? Actually, West Texas is a pretty good place. But really, any of these deserts shown on this map here are great places to go, and all of them have provided meteorites to us, especially the Chihuahua Desert in the southwest United States, the Atacama in Chile, the Sahara in North Africa, the Namib Desert in Namibia, the Taklamakan Desert, which is here in China, and then the Nullarbor Desert in central Australia. And we've been to several of these places looking for meteorites. This is a Namib Desert, a great place looking for meteorites. We were there in 1990. This is where the world's biggest meteorite is. Here it is right here. We're taking a nap on it down in the lower right. This is the Hoba Iron. And also there are meteorites. So here we are walking around the desert, and here's some scattered meteorites here on the surface. They're easy to spot because the sand here is kind of a buff color, and these meteorites have rusted and they're black. And if you really go to any desert on the Earth, you can probably find meteorites if you can recognize them. Of course, we had some problems down there, some problems with our truck, as you can see. But it's really fun doing this. Skipping ahead, the southwest United States. This is the Swabian Desert. This is actually in southeast New Mexico. And we just took a place, we took the map, walked around, and we found 2 meteorites on the same day, just walking around randomly. This is the Atacama Desert in Chile. This is probably the world's driest place. It's so dry, it's kind of scary, really. I could go on in detail about that. A lot of observatories out there, and this is in the Andes Mountains, next to the Andes Mountains. And there are a lot of observatories there because the air is so dry, it's really clear. It's almost like observing from the moon. But lots of meteorites out here too. Again, you see this desert here, buff-colored sand, and here's a black-colored meteorite sitting on the surface. And it was easy to spot from even many feet away. And since we were out there about 3 decades ago, hundreds of meteorites have been recovered from this desert. And by the way, this bottle here, next to my friend's foot, this is from the War of the Pacific, a war about the same time as the American Civil War. It took place, and they were fighting over phosphates out there. And so there's not a lot happening out there, as you can see. It's pretty deserted. No animals, no plants, no animals, no plants, no water, nothing, just meteorites and some old bottles. A great place, really. But the best place to find meteorites on the Earth is in Antarctica, down here at the bottom of the Earth. It's one of the driest places on Earth, and it's certainly the coldest and also the highest continent next to Africa. So all these things being very, very dry, especially, make it a great place to preserve meteorites. Now, meteorites don't preferentially fall here. They fall everywhere with equal amount. It's just that in Antarctica, there are no rivers to carry the rocks away. There's no liquid water, really, so to speak, to weather them away. And animals and plants aren't destroying them. So when meteorites fall here, they just stay put. Unless they fall on a glacier, then they just travel along with the ice. And so you can find areas out here, ice-covered areas, where you can find hundreds of meteorites in areas the size of your house sometimes. Over 40,000 meteorites have been recovered from Antarctica over the past 25 years, or actually 40 years. So you travel out here. People go almost every year from the United States, Europe, Japan, Korea, and China to go out looking for meteorites. You travel by sled and ski-doo. You live in tents, believe it or not, for 7 weeks out there in the polar plateau. It's an unforgiving place. If you like winter camping, it's great. If you like winter camping, it's like torture. And here you can see the bathroom. Here the tents where people are living, and here's the bathroom. The entire outside is the bathroom. So anyway, I'll say more about that. But you see, it's quite a beautiful place. Here we are looking for meteorites on the ice. It looks like we're floating on a river, on a lake or something. And these mountains in the background here are actually 10,000 feet high and about 50 miles away. It looks a lot closer and shorter. It's because the air is so dry there that distances are really deceiving. So here's a meteorite on the ice. As you can see, looking around, they're easy to spot because they're about the only things on the ice that aren't ice. In many places in Antarctica, the only rocks you see are meteorites. Again, I've seen areas the size of maybe your house or your apartment building with hundreds of meteorites just sitting there to be picked up. It's really great. And here's the biggest meteorite we ever found. This was found in 1986, about 400 pounds, and sitting on snow. Pretty cool meteorite. Actually, it's a pretty boring meteorite, but exciting because it was so big. So every year we go down there and collect hundreds to thousands of meteorites every year, and they come back to a laboratory in Houston, which again is very, very clean. They're brought back still frozen, wrapped up in Antarctica. They're carried back still frozen. They're frozen. Then they're thawed out gradually in nitrogen cabinets to minimize contamination. Then they're broken open and studied by scientists worldwide. It's pretty cool. And more than half the meteorites we have in laboratories and museums now come from Antarctica, found in Antarctica. So it's really been a great source of meteorites for us. And again, you might ask, why do we need 70,000 meteorites? Wouldn't 10 do, right? Well, the fact is that these, say, 70 or 80,000 meteorites we have so far probably only come from about 100 places, 100 worlds. And there are over 1 million possible worlds that meteorites could be coming from. There are asteroids, the moon, Mars, maybe other planets, which means that we've only sampled, really just barely sampled what's out there in space by meteorites. And every year we find meteorites that are from new worlds. Every year meteorites fall or we find them, and they're totally different from previous ones. And so it's not like we're finding them from the same place year after year. These meteorite expeditions are really bringing us samples from new worlds every year. So talk about meteorites and asteroids a little bit here, but the solar system doesn't end with the planets. It goes a little further out. There are comets. Now, comets orbiting among the planets, also way out beyond the planets, and they're constantly changing and evolving. They're very interesting because they obviously contain a lot of volatiles, which is why they have this coma, this tail you see. And that means that they formed way out beyond the giant planets, way out when the planets were still forming, in fact. And they preserve water, organics, materials from the dawn of the solar system. And probably comets were the objects that brought water and all the organics to the Earth. So all the raw materials for life arrived on the Earth and other planets in comets. And so they're really of interest to us as well. And here just shows the orbit of a typical comet. Here's the Earth, and here's some giant planets, Jupiter and Saturn. And most comets are orbiting in very highly elliptical orbits and go way out beyond the planets and orbit in again. Some are orbiting in the inner solar system, but many of them are orbiting with orbits like this. Distances, thousands of Earth-Sun distances, and AU is the Earth-Sun distance. Many of these comets have AUs of thousands of Earth-Sun distances. And in fact, from the orbits of comets, it seems as though there is actually a disk of comets orbiting the sun, but far out away from the planets. I mean, this shows the orbits of there's the sun in the center here, there's the planets in here, but way out, tens of thousands of Earth-Sun distances, there's a cloud, an entire sphere of comets orbiting around the sun. As you get closer to the sun, the sphere pinches down to a disk of comets like this. And so the disk of comets, the ones that are orbiting in the plane of the planets, these are the short period comets, like Halley's Comet, the comets you've heard about, that appear every few tens of years or years, and then they're gone again. But the comets that orbit out here, these are about a third of the way to the nearest star, other star. These are way out far from the sun. And these comets might never, ever come into the inner solar system. They might just orbit their entire lifetimes out this far away. And they occasionally will get perturbed and then become long period comets that you might just see once in thousands of years. And these aren't really, these used to be hypothetical, but in fact, people have now seen Oort clouds around other stars. This is an image of an Oort cloud, a radio image of an Oort cloud around the star HD 181327. This is a really catchy name. This is seen by radar imaging. So this is a image of the, not image, it's a cartoon of the star, central star, HD 181327. These are the orbits of planets, distances of planets in our solar system. And then here's this orbit of the Oort cloud, which you can see in radar imaging. They're actually imaging dust and small bodies far from this star. So this is an image of an Oort cloud around another star. And the same thing happens for our solar system as well. So we had missions that went out to collect comet dust. There have been two so far. And the first one was a long time ago, 1984 to 90. First mission I worked on, it was the brainchild of this guy, Bill Kynard, who was at NASA Langley. And this was a bus-sized satellite. It was the size of a city bus, which had more than 100 experiments on board, including experiments to capture comet dust. And it was launched by one shuttle, recovered by another shuttle, back in the late 80s, early 90s. It's pretty cool. And we basically looked at this entire satellite and recovered grains of comet dust that impacted on these experiments during the 5 years it was in orbit. We found more than 10,000 impacts like this on that satellite. Pretty cool. Here we are looking at satellite in a clean room in the Kennedy Space Center. And here's an impact on a piece of glass, as a matter of fact. This is a metal coated piece of glass. An impact. This is about a centimeter across from left to right. And there were 10,000 of these peppering the entire spacecraft. Here's on the upper right is a piece of glass that was shattered by an impact of a micrometeorite. So then we had a mission that went out just to collect stardust, rather comet dust, called the Stardust mission. And this mission, the heart of the mission was a collector, but the size of a tennis racket, with silica aerogel plates, which is a very, very low density material like window glass, but lighter than anything else that we know. That was put out in this tray here. Here's the tray being loaded into the capsule, and this tray was extended as the spacecraft passed by a comet. It launched in 1999 on the little Delta rocket, orbited around the Earth, and passed by this comet called Wilt 2, not a very famous comet at the time. In fact, Paul Wilt's still alive, the person who discovered it. And this comet had an orbit that took it out to the orbit of Jupiter. The red ellipse here. Jupiter's orbit is here, and then brought it by the Earth orbit, which is here. And so this comet was formed out in the giant planets, but its orbit carried it in close enough to be captured easily by a spacecraft. So in 2004, 20 years ago, the spacecraft passed by the comet. Actually, the comet passed by the spacecraft, and grains of dust from the comet smacked into this tray of aerogel, looks like a tennis racket here, sticking up out of the spacecraft. And we got thousands of impact of grains from the comet from this mission. And here's the picture of the comet nucleus, only about 5 kilometers across, pretty small. In fact, you could easily walk around in a single day, no problem, it's that small. You see jets of dust and gas coming out of the comet, and that's what we sampled. And here we are in the clean room in JSC. This clean room is about 1,000 times cleaner than the lunar lab, because we're worried about contamination from organics and dust. We're opening it up here. And here's the tray after it came back. Looks like it's pretty clean, in fact, but at close examination, you see thousands of impacts like this one right here, where a grain of comet dust smacked into the aerogel, and the grains are trapped in the aerogel, and now we can pluck them out for analysis. And here's some tracks viewed on the side. So in this case, the aerogel pieces are here, and the impacts were from the left to right. So grains would come in, smash into the aerogel, rip apart, and these little grains at the end of these tracks. I'm pointing to some right now. So these are comet grains, 4.5 billion years old, trapped in aerogel. And so in this clean lab now, we go in and carve out pieces of aerogel and pull out the samples for analysis. And you might wonder, couldn't you do these analyses at the comet using the spacecraft? And the answer is you can do some analyses that way, but mostly you can't. I mean, a lot of the analysis tools we use are using instruments that are too big to fly in space. In fact, here's an instrument we use in Japan. It's the size of a mountain. Here's a mountain in Japan, and here's the instrument wrapped around the mountain. It's called a synchrotron lab. It's for making very, very high energy X-rays. And the experiments are around the side of the mountain, and you make the analyses using this entire instrument, and you move around this here using a little bicycle down here on the right. It's so large that you use a bicycle to get around in the lab. But you can imagine you can ever fly something in space. You can only do these analyses on the ground. So the value of having samples on the ground is you can do the analysis using in the instrument, and you can use instruments that haven't been invented when you collect the samples. And here's a cool thing. This is one of the grains collected at the comet. This is a slice, a very thin slice prepared for analysis. And this is about 50 micrometers across, which means a human hair sliced it in cross section would be larger than the field of view of this entire screen. So these are smaller in diameter than a human hair. And here in this material on the right, a close up on the right here, this is a little sphere of hydrocarbon. little hydrocarbon globule. And these are all over the place in these primitive solar system samples. So these are very similar to soap suds and soap bubbles. These are perfect places for chemical reactions to occur. And so the early Earth would have had these things arriving on it from comets all the time. Imagine the first oceans on the Earth would have been covered with an oil slick with these little spheres floating there. And you can imagine organic reactions occurring inside of these. These would have been ready-made homes for organic reactions. And I'll skip by this. One cool thing we found on the mission was we found grains that had been formed close to the sun, and they had popped out the outer part of the solar disk to be accreted into the comet. In other words, we had thought the comet would have formed. This is a cartoon of our early solar disk around our early forming sun, and the planets would be forming in here in these little rings of dust swirling around the early star. These are jets of energy escaping from the sun when it first turned on. And way out here, where it's cold and dark, far from the sun, where comets are forming. You know that they contain so many organics and fluid and water, CO2, things like that, very volatile gases. And we thought that's where everything in a comet would have formed, and we were wrong. We found from this mission was that a lot of the grains formed right up next to the sun, because they're very high temperature materials, must have been ejected out or skipped out to the place where the comet then was accumulated. So rather than sampling only the outer part of the early solar nebula, comets apparently sample the entire solar nebula in one go. That was a huge surprise from this mission. There's a mission NASA put up to collect solar wind from our sun, determine the composition of the sun. It was called the Genesis mission, and this flew hundreds of these very, very clean silicon, gold, silver wafer spinel, ruby wafers to collect atoms from the sun. It unfortunately crashed on return to Earth, but they were still able to make analyses of these little pieces of these cells, and in the lab analyze the sun. That still happened. It took years longer because it broke on landing on the Earth, but they were able to still recover all these little pieces of these little cells and extract the solar atoms out of those pieces of material and make those analyses. So even things go wrong, you can still learn a lot from these missions. They recovered all the science from the mission, even though it had a kind of a disastrous crash at the end. There have been three missions recently to asteroids, primitive asteroids. The first was the Hayabusa mission, which is mainly a Japanese mission with scientists from America, Europe, and Australia on board. This is the model of spacecraft, and here's the science team here standing around it. This is me here. This is like a long time ago. This mission went out and returned dust from this asteroid called Itokawa. Itokawa was kind of the founding father of the Japanese space agency, and it's pretty small. On the right, this is a space station for scale. So it's a space station sized small object. Looks like an otter kind of. And this spacecraft went out, landed several times, and took off with samples of dust from the asteroid. Returned not to the US, but to Australia 13 years ago. And here it is on the ground. Here's me, my Australian Outback hat, right? Three guys from a bomb squad in case we had to blow up the spacecraft. It's a long story. And this guy here, he's a scientist from Australia. His job was to destroy the spacecraft in case it had breached and there was any possibility of contamination of deadly organics from space. The Australians were concerned that the spacecraft might have brought back deadly bacteria from the asteroid. And if it was found to be opened on the ground, his plan was to cover it with a spermicidal material to kill all the germs. Luckily, it didn't happen. And we didn't find any organics in anyway, but it wasn't a menace to society. We just picked it up and carried it back to Japan. And here in the lab, here I am actually here with my Japanese friends. We're analyzing the samples in their clean room to discover what these samples are like. And the cool thing here was these are pictures of some of the grains. Again, they're really tiny. Here's a 25 micron scale bar, and the human hair is about this big in diameter. So again, these are smaller than a human hair in diameter, but easily analyzed by instruments in the lab on the Earth. And we found was a record of the history of these grains locked in these samples, including how intense the early sun had been when it first turned on, because these grains contain atoms from the sun implanted into them during the sun's history. We'll go on past this quickly. Next mission was the Hayabusa 2 mission, which just was completed a couple of years ago. This is a follow-on mission to a more primitive organic-rich asteroid. Looks like the first Hayabusa mission landed, collected dust from the asteroid. This is the asteroid it visited, asteroid Ryugu. Looks like a spinning top. It's only about 1 kilometer in diameter, pretty small again. These are all small objects. It's a beanbag of just loose rocks and dust just held together by very weak gravity. So if you were standing on this asteroid, you could just burrow into it with your fingers and dig right through it. If you're running on it, the gravity is so small, you actually could jump off the asteroid and then leave orbit and leave the asteroid. So it's actually be very careful walking on these objects, because if you walk too fast, you go into either orbit or you go out into space. Anyway, here's a movie of the collection of dust on the asteroid surface. This foot plunges down the surface and smacks in the surface and startled a gun, which released a lot of dust and rock, which was collected and brought back. Pretty cool. Return to Australia again. Here's the capsule on the ground. Here's the guys, the bomb shelter guys again, just in case. And here's some of the sample. This time they collected about 5 grams of sample, which is a whole lot of sample actually. And we're analyzing those samples still today. One cool thing we found was an iron sulfide crystal we recovered from this sample. We mounted it and analyzed it in an ion microprobe, and we found these little holes. This is like a CAT scan of this sample. And as you scan down through it, you get X-ray images of the sample. You can see holes inside of it, and those holes held liquid water and liquid CO2. Here's our images of analyses of these fluids trapped inside this iron sulfide. And there was water in there. There was carbon dioxide. There was chlorine. There was cyanide, hydrogen cyanide compounds, all kinds of organics, water, and carbon dioxide. So these are fluids from the very dawn of the solar system, which have been preserved in these tiny little grains for analysis today. So these are our trapped samples of the fluids that would have come to the early Earth. And I'll skip ahead here. The last 2 missions are the OSIRIS-REx mission, which is a very expensive mission the U.S. launched to another organic-rich asteroid, and it's returning right now. It went to an asteroid Bennu, which is a lot like asteroid Ryugu, a little small, half the size of Ryugu. Again, it's a beanbag of loose rock and dust. And those samples are coming back. This is a picture of the asteroid's surface. You can see loose rock sitting here. Again, it's not a solid object. It's just a loose beanbag of rock and dust. The spacecraft landed a couple of times and sampled, I think, 50 grams or 500 grams, 50 grams of sample, about 10 times as much as we got from the Hayabusa 2 mission. Probably the very similar kind of material coming back. And this spacecraft lands back on the Earth in 2 more months. So in the fall, in September, it lands with its samples in Utah, and we'll see what we learn from that one. And the last mission is a mission that launches next year. It's called the Mars Moons Exploration Mission. It's mainly, again, a Japanese mission, but there's a lot of scientists from the US, Australia, Europe on there. And this is going to travel out to the moons of Mars. Here's Mars on the left here. Mars has 2 moons. They're pretty unusual. They're very small, and they're orbiting very close to Mars. So close, they're actually going to enter and crash into Mars in about 10 million years. And the biggest of these is Phobos, which is a very animatic object. And it's the goal of this mission, which will launch next year, will be to travel to Phobos and land twice and collect samples from Phobos and bring them back to Earth. And Phobos is a very strange object. We haven't got time to talk about it much here, but it's got such a strange composition as far as you can tell from spectroscopy, looking at it from far away. And its orbit is so unusual. You can't tell if it formed around Mars like the Earth's moon formed around the Earth, or if it was a captured asteroid or comet. You can't tell. And so we'll find that out. The samples, if the spacecraft launches on time next year, these samples will be back in 2029. They'll also land in Australia, hopefully not carrying deadly organics. And we'll find out how this moon formed. And there's a good chance that impacts, asteroids and comets striking Mars would knock materials onto Phobos. This Phobos orbits so close to the surface of Mars. Those missions very well could return samples from Mars as well. So this will be our first samples from the Mars system that we curated aside from Martian meteorites. And I think that's the last slide I have. So I'll stop.